The Nanome is the name of a project being conducted at the National Research Council labs on the University of Alberta campus in Edmonton. And the aim of this project is to build, design, characterize a modular electron microscope that can be built in any research lab that has a machine shop attached to it. We are particularly interested in people who want to build an instrument to go along with other vacuum equipment. And so we're designing something that is compatible with standard vacuum equipment. And we're going to make all the construction details and all of the results that we get on the prototype available to anyone if they want to copy what we've done or even modify it. A secondary goal is to develop expertise in practical electron optics, which nowadays is largely confined to a small number of commercial companies. And as part of this, it is providing training for both undergraduate and graduate students at the University of Alberta and elsewhere. Now, if you think about building an electron microscope from the ground up, there are some decisions that you have to make. Do you use magnetic or electrostatic lenses to focus the electrons? Do you have the electron source or the specimen at ground potential? And are you going to have a horizontal or a vertical lens column? And we're used to the idea that electron microscopes are vertical, but there was something called the horizontal electron microscope that Philips put onto the market quite successfully, I think. It really wasn't horizontal because the electron column was something like at a 45-degree angle. And the observer would sit in front of this screen. It's a transmission screen. So it's really like sitting in front of a giant oscilloscope. If you want a column that is truly horizontal, then you have to go back to the very early days of electron microscopy. Here's an instrument in Professor Marton's lab in Brussels. And on the right-hand side of the picture, electrons are emitted from a heated filament. They're accelerated and pass through lenses. And then they form an image on a screen, transmission screen towards the left. And that screen was photographed by the bellows camera that you see on the far left there. So the equipment consists of the lens column, vacuum equipment to remove the air from the column, and power supplies for the lenses and for the high voltage. And if you're building a transmission electron microscope, then you have to have a specimen that's sufficiently thin, fraction of a micron, but also you need the electrons traveling sufficiently fast to go through the specimen without absorption. And that means that you have to accelerate the electrons to a speed, a substantial fraction of the speed of light, and that requires an accelerating voltage of some tens of kilovolts. One advantage in applying this high voltage is that it gives us a de Broglie wavelength for the electrons, which is a fraction of an angstrom unit. In other words, it's smaller than an atom. So in principle, if there are no lens aberrations, it will be possible to resolve single atoms. Now, in general, this kind of equipment has the lens column and the specimen at ground potential. And that has the obvious advantage in terms of convenience and safety that most of the equipment is at ground potential. That means the electron source is at a high negative potential. Usually it's at the top of the instrument, and so the high potential is up at the top, away from where the operator sits. And the electrons are accelerated from this negative potential up to ground potential. they're accelerated towards what is called an anode plate, which contains a central hole, small hole. Most of the electrons do not go through the hole, and so the emission current from the filament is orders of magnitude greater than the actual beam current. And what that means is that the power supply for the high voltage has to be capable of supplying an appreciable current, typically tens of microns. Now, the lenses themselves could make use of either electrostatic or magnetic forces to focus the electrons. And the verdict of history seems to be that for electron columns, it's better to use magnetic lenses. And there are some fairly obvious reasons for that. One is that you don't need any high voltage applied to the lenses. The lenses carry an appreciable current, but not appreciable voltage. And so problems of high voltage insulation in the column are avoided, and problems of discharge in the column are avoided. The other big advantage of magnetic lenses is that, well, if you consider electrostatic lenses, it turns out to be difficult to get a coefficient of spherical aberration less than about twice the focal length of the lens. Whereas for magnetic lenses, it is possible to have CS less than the focal length of the lens if you construct a strong lens with a small focal length of the order of a millimeter. And this is important in connection with what we call the objective lens in either a TEM or a STEM instrument. It's the lens closest to the specimen, and it's the lens that determines more than the other lenses the spatial resolution of the whole instrument. And so if we have a focal length of the order of a millimeter, that means that the specimen has to be within a millimeter or two of the center of the lens. So really, the specimen is in the lens field, in the magnetic field of the lens. Now, you can do the same kind of thing with an electrostatic objective lens, but that means the specimen is sitting within an electrostatic field. And if the specimen is electrically conducting, that will short out the field, distort the field, and you'll lose your focusing. Now, of course, the same thing happens with a magnetic lens if you have a strongly magnetic specimen, ferromagnetic specimen. But ferromagnetic specimens are much less common than conducting specimens. And so I think this is the major reason why magnetic lenses have been used for specimens of all kinds. And it's basically dictated by this requirement for high spatial resolution, small focal length objective lens. And if we take a look at how a magnetic lens actually works, we're making use of the Lorentz force, which is perpendicular to the velocity vector v of the electron and perpendicular to the magnetic induction B. So if an electron is going along the optic axis, which is horizontal in these diagrams, the force is actually zero, which is what we want, because we want the electrons to continue along the optic axis without being deflected. If, on the other hand, we have a radial component of velocity, let's say upwards on the diagram on the left, that component of velocity together with the horizontal magnetic field will give us a force that is out of the plane of the diagram. So the first thing that happens is that the electron starts moving in a circle. It spirals through the magnetic field. Once we have that perpendicular component of motion, then that component of V combined with the magnetic field along the axis gives us a force back towards the optic axis. And so we have our electron deviating from the axis and then focused back towards the axis, and that's the basis of the focusing action. We can make it more efficient by surrounding the windings which provide this magnetic field with ferromagnetic material, with a small gap that concentrates all the magnetic field into a region a few millimeters cubed on the optic axis. And for high resolution, all the instruments that I know of make use of magnetic lenses, including this instrument at Professor Crew's lab in Chicago, the first instrument to image individual atoms, heavy atoms such as uranium. It was a scanning transmission microscope, and so the image is obtained by forming a very small diameter electron beam and scanning that across the specimen. Although it's not immediately obvious from the picture, the lenses were magnetic. The objective lens was actually a quadrupole magnetic lens. And in the commercial field, instruments between about 1960 and the present day, which are illustrated here, have used magnetic lenses, and the resolution has gradually improved from something like 7 angstroms to a fraction of an angstrom. And that improvement is due to improvements in machining of lenses, design of the column, the stability of the column, stability of power supplies, and also increasing the accelerating voltage from something like 60 kilovolts in early instruments up to as much as 300 kilovolts in modern instruments. And that gives you less than an angstrom, better than an angstrom spatial resolution. And in fact, on the recent instruments, as I'm sure you're aware, part of the improvement is in terms of correcting aberrations. Maybe 20 years ago, it was found out how to correct the aberrations of magnetic lenses in a reliable way. And that aberration correction, combined with high electrical stability, high mechanical stability, and control of the environment in the electron microscope room, has given us instruments that are capable of fairly routinely giving a resolution below 1 angstrom. So you might ask, if you can buy such an instrument, why would you even think of building an electron microscope of your own? Well, several reasons. One is that those kind of high resolution instruments are expensive. We're talking about millions of pounds or euros or dollars. And these are instruments that have proprietary parts. It's very difficult nowadays to do your own servicing on a modern microscope. Therefore, you need a service contract, and service contracts are correspondingly expensive. If you do want to modify the microscope in any way, that may create problems in terms of voiding the warranty. So our aim in the NanoMi project was to relax this requirement on resolution. We're aiming initially at a resolution of 10 nanometers, 100 times worse than the best TEMs of today, but a factor of 50 better than a light microscope. And in fact, this 10 nanometer resolution was the kind of resolution that was obtainable on the best commercial SEMs for many years in the 1970s, 1980s. And during that period of time, 10 nanometer resolution was sufficient for solving many materials problems. So because we've relaxed the requirement on resolution, we can take another look at this question of electrostatic or magnetic lenses. And in fact, our decision was to look into electrostatic lenses. And there are some advantages in terms of electrostatic lenses. They consume no power, which means that the lenses do not need water cooling. That's an advantage if you want to put a lens column inside a vacuum system that may have other components associated with it. Electrostatic lenses don't rotate the image. That's not really a major advantage. But another advantage is that the stability of the power supply can be less with electrostatic lenses. And the reason for that is that if you use the same power supply to accelerate the electrons and to drive the lenses, if the voltage increases, the electrons are traveling faster, that would make the focusing less strong. But if you have the voltage applied also to the lenses, the focusing is compensated. So you have a system which is relatively insensitive to first order to the voltage of the lenses and the accelerating voltage. And so we have in mind to devise a voltage divider system that would allow a single power supply, which would reduce the cost and maybe help with the stability of the instrument. Now, if we wanted a better resolution, then sometime in the future, there is the option that we could have an objective lens magnetic, but with a permanent magnet, again, avoiding the need for water cooling. And there are precedents for having a permanent magnet objective lens. In fact, there was a machine marketed by RCA around 1950, marketed as a desktop electron microscope with just 2 lenses, and both of those lenses used permanent magnets. The accelerating voltage apparently was as high as 50 kV, and the resolution claimed was 10 nanometers. If we take a look at how electrostatic lens works, it's rather simple compared to a magnetic lens. We're using the fact that the force is proportional to the electric field, and the electric field is generated by a voltage applied to a single electrode. That's the central electrode in the center here. We apply a negative voltage of the same order of magnitude as the voltage that we use to accelerate the electrons. The 2 electrodes to the left and the right are at ground potential, and their function is simply to shape the electrostatic field and to confine that field within the region of the central electrode. Since there's only one electrode with a voltage applied, it's called an Einzel lens. And these lenses are currently used in photoelectron microscopes, low energy electron microscopes, where we're talking about 10 kV accelerating potential typically. Electrostatic lenses are also used in space probes, where weight is a prime consideration. They're also used in ion columns, such as a fib machine, because the magnetic field is proportional to speed of the charged particle, and ions travel much slower than electrons for a given accelerating potential. And so it's inefficient to focus electrons with magnetic fields. Instead, a fib machine has an electrostatic column. And if you go back in history, electrostatic lenses were used in oscilloscopes. They were used in television sets up to maybe 20 years ago, and also in early SEM and TEM instruments. Here's a scanning electron microscope marketed by RCA around the 1940s, and the lens column was electrostatic. And the early experiments backing up this principle were done with little tubes that you see on the bottom left, essentially miniature cathode ray tubes, using, again, electrostatic lenses. There was one TEM marketed with electrostatic lenses by a group of engineers who left the Tektronix company and formed a company called Electros in the early 1970s. One of those employees was Gert Refer, shown on the right-hand side in the basement of a home in Oregon. When the company folded up, she acquired 3 of these electron microscopes together with spare parts and manuals, and these eventually ended up in museums, labs, various places. You can see a fan cooling the diffusion pump of the microscope. So there was no cooling water required for lenses or for anything in this equipment. The accelerating voltage was 40 kV. The resolution was of the order of a nanometer, and it did have some quite advanced features such as stereo imaging. Now, NanoMi is going to use electrostatic lenses with an accelerating voltage at the most 50 kilovolts, because you can buy relatively inexpensive power supplies that go up to that value. We have in-house piezo drivers for sample and aperture motion, and the idea is to have the control of the electronics all by a single computer, and to use vacuum hardware based on ConFlat design, which is relatively inexpensive these days and compatible with other vacuum equipment, including UHV. So we're talking about this kind of equipment. Here's a complicated example at Cornell University, but our ConFlat arrangement is much more simple. As you can see on the left-hand side, we have a turbomolecular pump connected with these ConFlat flanges to a vertical column. It's all using this stainless steel ConFlat architecture. And on the right-hand side, the internal parts of the column, the electron source is at the bottom. The turbomolecular pump gives us a vacuum 10 to the minus 7 torr within quite a short period of time. Now, we wanted to start off with a thermionic electron source, just a heated filament. And so the idea was to take a commercial thermionic source. We don't want to reinvent the wheel when it's not necessary. And so we thought that at least we will be guaranteed of an electron beam without any problems. There were, in fact, problems, and in the form of wires inside the microscope melting after a period of hours. And we, of course, attributed this to overheating, and a student did a simulation of what the temperature ought to be when you reach equilibrium. So this diagram on the left-hand side is showing that the gun itself goes up to a temperature something like 300, 400 degrees, because the supports for the gun were made of a material that had relatively poor thermal conductivity. And the simulations agreed with experiment, namely that it took a few hours for the temperature to go up to a few hundred degrees. The solution was simply to replace those supports with a material that has good thermal conductivity. And that material is Shatner-LM, which is a boron nitride, aluminum nitride composite, which is a good thermal conductor, but a good electrical insulator. And then the simulations told us that the temperature remains within 100 degrees, and that's sufficient. Now, an electrostatic lens is basically simple, has 3 electrodes. The pink electrode here is the one to which a negative voltage is applied. And it's supported by an insulator, which is the yellow structure. And you'll notice that it's corrugated, because the main problem with electrostatic lenses is breakdown, electrical breakdown within the lens. And that breakdown usually occurs as surface breakdown. And that process can be avoided or hindered by making the surface area as large as possible, the path between the negative voltage and the ground as large as possible. And so the insulator here is corrugated for the same reason that electrical pylons have their insulators corrugated. So here are some designs of electrostatic lenses based on principles in a paper by Gert Renfer. Parameters that affect the focusing are, of course, the amount of negative potential applied, but also the internal diameter, D and A, of the electrodes, and the spacing, S and T, of the electrodes along the optic axis. And so we designed one lens which was symmetrical, another lens which is asymmetrical and has this corrugated insulator structure. In order to characterize these lenses experimentally, we used a procedure that is described in a paper by Renfer et al. And that consists of placing within the optical column a mesh, and a TN grid works quite well, at a known position from a beam crossover. And then depending on whether that mesh is upstream or downstream of the crossover, you get an image. It's actually a shadow graph, an out of focus image, which tells you from the spacing of the grid bars what is the focal length of the lens, and from the curvature of those grid bars, in other words, the distortion in the image, you can get an estimate for the spherical aberration coefficient. And here's a graph with 3 experimental points, red, blue, and green, of the focal length as a function of the voltage applied to the lens. And you can see that we have to apply a voltage approaching the accelerating voltage of the electrons. And the 3 experimental points agree reasonably well with simulations of what the focusing property of these electrostatic lenses should be. And here are a couple of images just with a single lens operating, a transmission image of a grid on the left, and a secondary electron image obtained when we added a secondary electron detector to the side of the column. And here is the kind of arrangement that we have. If we want 3 lenses, then we're going to stack these vertically, supported by rods which ensure that the lenses, to a first approximation, are properly aligned. But anyone who works with electron instruments knows that for high energy electron beams, electrons cannot stray far from the optic axis without incurring severe aberrations. And so it's likely that we're going to need some fine tuning, some fine alignment of the electron lenses. In other words, we need electrical deflectors. We can't do the alignment mechanically because this is a lens system within a vacuum system. So we don't have access, mechanical access, or at least it would be inconvenient. Now, deflection for alignment purposes or scanning purposes can make use of magnetic fields, horizontal in this diagram. And if you need pure shift or pure tilt, you actually need a double deflection as shown in the diagram. The same kind of thing can be obtained with electrostatic deflectors, basically parallel plates. And you can do calculations of the electron trajectory within a double deflection system. So on the left, we've got a pure shift of the electron beam, and on the right-hand side, a tilt about a point within the lens system. And again, you have the choice between electrostatic or electromagnetic deflection. And electromagnetic deflection is fine. It's used in most electron microscopes. Power is not a problem, no water cooling needed because the amount of current is relatively small. But again, there are some advantages of electrostatic fields, particularly if you want to use these deflectors to scan the beam across the specimen. If you want to do that fast, as we know from oscilloscope use, you can scan much faster with electrostatic fields than with magnetic fields. And there is no magnetic hysteresis, which would be valuable if you want to have some kind of non-raster scan. Also, no power dissipation if you have electrostatic scanning, which might be useful if you want to scan over a large area at low magnification. Simulations tell us that with reasonable geometry, we will need, for an electrostatic deflector, voltages applied of the order of a few hundred volts, which is possible with solid state electronics. Here's a picture of some lenses constructed, machined at the NRC lab in Edmonton. The white, pinkish white color is Makor, which is a glass ceramic material. It's a good electrical insulator. It's stable up to hundreds of degrees centigrade in case you want to bake a system. And it's a reasonably good material to use, mechanically stable. Here is a ray diagram for a 3-lens optics, as you might need for a scanning electron microscope or a STEM machine, with 3 lenses between the electron source and the specimen. And on the bottom, cross-sectional diagram of the column. So on the left-hand side, we have our connection to the high voltage. We have the electron gun, a turbo pump to provide the vacuum, and electrons are accelerated towards the anode plate, which is at ground potential. Then we have our 3 lenses and a beam deflector to focus the electrons into a small spot on the sample. And of course, a secondary electron detector if you want to do secondary electron images. And in order to adjust the focus, we have a fluorescent screen at the far end of the column, which will form a Ronchigram, an out of focus shadow image of the specimen. That's useful if you want to do fine focusing of the electron beam on the sample. So that's basically as far as we have got in the project. Things have been slower than otherwise because of the COVID epidemic. So we've tried to compensate for that by having Zoom meetings every couple of weeks. And so here are some of the people involved on the project. As you can see, they are serious looking men, and the only female on our team, I've pasted a photograph of her on the bottom left and bottom right rather, and you'll see she's the only person smiling. Here is a more complete list of people involved in the project. Various people employed by the government at National Research Council, a couple of professors from University of Alberta, and a number of University of Alberta students have worked on this project, as well as students from the University of British Columbia. And this is a project, just a part-time project for these students. And in fact, all of these people are working only part-time on this project. They have many other things to do as part of their job. We have also got moral support from 2 of the microscope manufacturers, Hitachi and JEOL, and they are willing to give us advice if the need arises. Here's a picture of the building where the construction is taking place, and I've given on the right-hand side some contact information. We're putting all the information about our experiences, good and bad, on a website. And so all of the construction information will be available as an open science project. And I've put then there a couple of contact emails. You can certainly contact me, but if there's any detailed information you need, I suggest contacting Dr. Marek Malach at that email address at the University of Alberta. So thank you for listening, and I'd be happy to try and answer any questions.